All right, ready to go. Current slide. Now, before we get going on the slide here, let's just talk about what today's going to look like. It says on the thing we have class from 12 to 1:50, and then lab from 2 to 3:30. Well, I want to give you a full 2-hour lab because today's lab is maybe quite as long as the last one was, but it's still a long lab. So I want to give a full 2 hours for that. So that means from 1:30 to 3:30 we'll have labs. So we will have class only from now to 1:30, not 1:50. Okay? So stop me at 1:30 and say, let's get the lab going. Okay. Any questions before we get going today? Is anyone here today that wasn't here last time? I know some are. I did return labs and tests last time. Let me find those. Should have done this before I started the recording. See if I can get some things in some type of order here. Okay. That will be there. There. Lab. That is not here. Taylor's not here. Adam's here. Good. Okay. Test. Do test. That's about it. Sorry, I should have done that before. All right, I think we went over this before. Any questions on this part? Okay. Now, what we're going to do next was mark Monica here. I'm sorry, Christy here. Right. Yeah. I have 2 Monicas in my last 2 classes, so I'm stuck on Monica. Okay. Yeah, Christy's here. Okay, we went over these last time, and where we were going to start today, and we went over the meteor shower periods. We got one small one coming up just at the end of this term, between now and fall term. Perseid, I mean, it's a pretty good size one. It's the second largest we have, so keep that in mind for August 12th. All right, here were the pictures. Now, these aren't quite the same pictures you have in your text. These are from the older one. And by the way, I just happened to notice this, another one. They do have a picture in your text of a fairly close-up photo of an asteroid, okay? There was a spacecraft named Dawn obtained this image of Vesta back in 2011 from a distance of about 3,000 miles or so. The 3 vertically aligned craters on the left have been nicknamed the Snowman. You don't see it we don't have a slideshow of it, but it sure looks like a big, smallest, okay? So that's pretty interesting. Okay, the pictures you have in your text of meteorites are on figure 1519, the A and B part. Now, they don't quite look like this, and it's sort of hard to tell. but I think they do correspond to these two. A is a stony meteorite, okay? Now, frankly to me, that looks more ironish than stony, but they call it the stony meteorite. The smooth black, the smooth black surface, and in your text it's not nearly as black as this one is, okay, was melted by compression of the atmosphere. That sure is what appears to have happened here. As it came flying through the atmosphere, portions of this melted and then hardened again. This looks like probably where it made impact with the ground while it was still hot, and that's why it looks like it has grains in it. This part just cooled more rapidly without hitting the ground, and that's what made it shiny, or actually that's a glassy kind of look, because it cooled really, really quickly, and that's what gives it that look. Okay. On the B is an iron meteorite. To me, these look totally backwards. I would say this one looks more ironish than that one does. But one of the reasons that is, and in your book, actually, the one that's in your picture, it does look maybe a little more ironish because it's dark without the grayish kind of color. Okay? But the reason that this one and the one in your book, it says that it's been cut, polished, and etched with acid. And I think that's what causes this mess, is the etching with acid. You can't tell that's iron looking at this because it's been etched with acid, determining its thing. In your book, there's smaller patches. They almost look like snow on it. That's not snow. My best guess is where it's been etched with acid. The pattern indicates that the original material cooled from molten material over millions of years. That's pretty incredible. It seemed like it would cool a bit faster than that, not take millions of years to cool. But who knows? Okay. And then in your text, there's a time-lapse image of a meteor shower. Notice how all the streaks can be traced back to one central region. I've looked at this several times, and I'm not sure I see that. Okay, a lot of them can be, but there's some that just are almost perpendicular to the others. So I don't see where they get that that statement from. Okay, but they're saying a region, not a point, but a central region. So maybe that makes more sense. In other words, you can imagine kind of the path of where the things are, these are the remnants coming through that. Okay. I believe that's all on meteors and meteorites. Any questions? We just didn't have time to do this one last time. So now we're moving to 15.3, which is the origin of the solar system. Okay? 3 stages here. Okay? On this front. Okay? Origin of the solar system. Let's start with what they call the protoplanet nebular model. Okay? Now, what that means is before they were actually planets. Okay? There's still clouds of things. You know, things have gotten very hot and very disorderly. Okay? For a while, as the sun was forming, it was clouds of gases that get gravitationally attracted, getting closer and closer, more and more of the gases, hotter and hotter, more pressure, more temperature, until it reaches the point where it is hot enough for fusion to occur. When it gets that hot, then there's huge explosions outward. Okay? There's still gravitational attraction inward, huge explosions outward, and for a while, okay, things are really chaotic. It hasn't formed its equilibrium yet. It's blowing up and good. Now, remember, not all those gases were hydrogen or even helium. There were other things in there, many heavy elements from many earlier stars and supernovas are mixed in with all those gases, okay? Not huge chunks of them, but, you know, aerosols, you might say, of them, okay? And these things are getting blown up and moved around and variety of such. So this is your stage A. The concentration in one region of space as dust, even though there's some very heavy metals, gas, and chemical compounds, okay? Here is the sort of picture of that. That's this stage, okay? The sun is not the sun yet, or the star is not a star yet. It's still in the process of blowing up and pulling in and doing all sorts of things, and stuff gets sort of differentiated, okay? So you get concentrations in one region of space of the dust, gas, chemical compound. Enormous amount of it. You think the sun's going to form out of this, all the planets, all the moons, all the asteroids are going to form from this, and a lot of the meteors. And this is just showing the 4 inner planets: Mercury, Venus, Earth, and Mars. Okay? The others are all out there too, around out of this disk. Okay? Now, we're still in stage A. That's the first one there. Stage B. The sun is sort of settling down, but the stuff around there, the formulation of large rotating nebulae, that's this stuff. Okay? And this is where things tend to group and clump together. Gravitational contraction pulls things closer. Now, this is a dumb question to ask, you might think, and it probably is. Have you ever watched figure skating in the Winter Olympics? And you notice when the skaters go to make spins, they spin out. They do this, but when they tuck in, they spin a lot faster. Okay? It all has to do with rotational dynamics, rotational momentum. That's when the pulling in, they spin faster. So that's what's happening here. You had clumps of stuff out there, probably with some motion to it, and as the gravitational contraction, it's sort of like the arms get folded in and the spins pick up. Okay? So we're in stage B here. Most of the mass concentrates in the central protostar. It's still not quite a star yet, but getting close. The remaining material forms in this disk. Okay? And this is called the accretion disk. I'm not quite sure why, except that the stuff there sort of accretes together. I don't know. Okay. Is it Cassidy? Caleb. Okay. One of these days I'll get names and faces tied together. Okay. And that's 7. Yeah. Okay. So we're on approximately page 397 near the bottom of that page. We're in stage B, the origin of the solar system. Okay? The remaining material forms in this accretion disk. You see it was forming there even in stage A. Now most of the material is in that disk. There is some stuff, usually minor stuff, and way out there stuff that's not in this disk, but most of it is, or a lot of it is. Okay? The material in the accretion disk begins clumping. That's what we call this. That's when the gravitational contraction happens. Now they're talking mostly about the sun's gravitational contraction, but also the planets, or what will be planets, are also contracting. And the material in that begins clumping. Now I wish they'd have shown the outer planets too. Okay? Because if they had, you would see that Jupiter is enormous out there. And inside Jupiter is the asteroid belt, and Jupiter moving around like that. Remember, Jupiter moves pretty fast in its move around the sun. Let me see if I can get that in the table. It may be it's It spins pretty fast. Its orbital period, though, is not all that fast, but the spin is quite fast, and it is moving, though. And I bet you that while the others were clumping as Jupiter went around, it kept and it's not Jupiter yet, it's just a huge massive thing, it kept those asteroids from clumping the way the others did. Now, that's just a guess, that's a speculation, okay? The material in the accretion disk begins clumping, except for the asteroids. They clump into smaller clumps. Lots of smaller clumps, okay? So there's stage B. Stage C, the protosun becomes a star, or the protostar becomes a sun, whichever you want to say it. This time, see, I think they should have had still something looking like that, a little less so than here, and now it has become a star, okay? The solar ignition flare-up may have blown away the hydrogen and helium atmosphere of the inner planets, okay? This is Chikari, right? Okay. Now, remember when the sun was still forming as a protostar and having these massive eruptions, and attracting back again, probably some of those blew away the hydrogen and helium atmosphere of the inner planets. And that's why Jupiter, Saturn, Uranus, and Neptune all are mostly hydrogen and helium. We were left with trace gases, with the heavier gases, very little hydrogen or helium compared to the others, okay? But we have heavier gases, nitrogen, carbon dioxide, called green plants, oxygen, methane, So, those are gone. Mercury, no atmosphere. I mean, it blew everything away from it. Venus has a pretty dense atmosphere, but it's in fact much denser than Earth. It's not a very healthy atmosphere. Earth has a really nice atmosphere. Mars still doesn't have much. Okay? And remember, some of the planets around, especially Saturn, actually have atmospheres too, because they picked up some of that that got blown away probably. Okay. Now, the protoplanets, the protosun has become a star. We're not quite planets yet, but they are heating up, or they're hot anyway, because they've been residue of nuclear explosion blowing things out. But now they separate the heavier materials from the lighter materials because they're liquid, okay? It's sort of like a centrifuge. The heavier stuff settles out on the inside, and the lighter stuff on the outside. And sure enough, our planet, the core is mostly iron and nickel, and further out in the crust, you get your silicates, which are much lighter materials, okay? So the protoplanets have heated, separating heavy and light minerals. The larger bodies cooled slower, with the heavier materials settling over longer periods of time into the central cores. Jupiter. Remember, it's mostly gases out here, certainly in the atmosphere and on the surface and deep. But in the core, it's iron silicate. So that has settled out more slowly in the central cores. To a lesser extent, the stuff from Earth, iron and nickel in the inner core, and then your silicates outside of that. Okay? These stages took a long, long time. Okay? The sun formed, they think, about 5.8 billion, 6 billion, something like that, 5 billion, somewhere in that years ago. The planets probably took a little bit longer because they were still hot and bothered, you might say. still forming up. And it was probably sometime like that. This is just my guess. Remember, the planets are heating. They're probably balls of liquid because they're so stinking hot, you know. And that may be the time that something impacted the Earth and broke off the moon. Because if it was liquid, that wasn't a fierce break. And they both turned spherical, so they must have been liquid, you know, if the break happened. Okay? That may be also when Venus got hit and started spinning backwards because of that. But it was still a mass of very hot liquids. Okay? So that would affect that, but it wouldn't permanently distort it. So there's your stage C. Any questions? Origin of the solar system. Okay? Now, here are ideas that developed over time. We've talked about the ancients and how they looked up at the skies and they followed the pattern far more than we do, okay? Followed the pattern of the stars, followed the sequences of the stars, followed, you know, the moon, the planets. Planets were really confusing. But everything seemed to center around the Earth. They seemed to go around the Earth. That celestial sphere seemed to move very slowly around the Earth. So, the earliest models were geocentric, Earth-centered models. It looks like the sun rises in the east, goes across the sky, and sets in the west. Looks like that. Looks like the sun's moving around us. We know today it isn't, but it looks that way. Okay? So the attempt of the early Greek astronomers and philosophers to explain the observed motion of the sun, moon, and stars. Okay? The stars were pretty easy. They were very regular. The sun was pretty regular too, but it didn't quite match the stars as well. So they had to put the stars way out there on one sphere, and then the sun on a different sphere going at a slightly different speed. The moon was a bit worse. Okay, they had to have it on another sphere moving its own way. They placed the Earth at the center of the orbit of all that. The problems were those stinking planets. Okay, they didn't obey the same rules. Certainly the stars, not even the sun, or even close to the moon. In fact, the word for planet meant wanderer, because they'd be tracking it across the sky, all the stars moving very regularly. The planets would look like they're moving regularly until suddenly one would sort of move backwards for a while and then turn around and move back in another direction. What is it doing there? Okay? So the exceptions for this model were explained by the Ptolemaic system. Boy, Ptolemy, I think is how you say his name. I believe, if I'm not mistaken, he was Egyptian. Okay? Lauren's here. By the way, I forgot this earlier, because I had given these out last time, but I forgot to tell some of you that I had done so. Let me get your labs. I should just wait till the end, but it's on you. Everybody else has theirs already, the labs and the tests. This was the best class ever for getting labs and tests in that first time. Keep it up. Okay. What's that? Oh, did you not get yours? Okay. That's what I was asking. Sorry. Insurance. There you are. Now the only person that hasn't gotten it is Guy. Okay. So Ptolemy really put together, the trouble was it's a very complicated system, but it seemed to explain most of these exceptions, the things that were out of whack. But over time, because all Ptolemy did was look at past and present stuff and fix a system that took care of that. But you see, he couldn't project what was going to happen in the future. And when future came, the system grew, inconsistency grew, and became complicated to explain. Because his model was wrong. He couldn't explain it with that model. Now, I hate that this kind of stuff happened, but the roots in that model were based on church beliefs. I don't like the way they say that, because Ptolemy and these others, they were part of the church. The church adopted those things and then built that into their theology, you might say, and then when the model broke down, they still wanted to keep the things the same. Yeah.
So exactly what model was doing when it was complicated?
Say that again.
Model was making it complicated.
What about complex?
You say it was complicated.
Yeah.
Which one was it?
It was Ptolemy's. I mean, in order to get everything to fit, you had to have more and more exceptions and more. Well, but then this happened, this is doing, and stuff, and it just got to be unwieldy because he was trying to account for more and more things that his model was failing on. You couldn't possibly do it, okay? But the problem was the church took the scriptures and tried to match them up with the model and made that, tried to blend them together. Well, when the model failed, then it made it obvious they were using wrong interpretation of the scriptures. And they didn't want to say they were wrong. So the honchos didn't want to change because they really did think, as most teenagers think, that they're center of the universe, right? I didn't say that, did I? Okay. Okay. But we really did. That was the general belief. In fact, I think I still see that in some beliefs too. But anyway, that's what made this so hard to question and to change. Okay? Now, there is a figure in your text they didn't show on the slides here. They kind of get close to it up there, but not the same. Compared to the stars and other things, this shows Mars. Mars starts tracking across the sky like this at different speeds from the stars, but then night after night after night, and then suddenly, not suddenly, but gradually, it goes back and tracks backwards against the stars, and then turns again and tracks this way against the stars, and goes back almost like it was going before. Why that aberration? Why did Mars do that, That's why the planets were called wonders, okay? Well, the reason is their model didn't work, okay? And here is basically another way of looking at this. Your book has a slightly different figure from this, but it still gets the same idea. Okay, let's. So the geocentric model over time just got worse and worse. They had to keep adjusting and revising and trying to make it more complicated to make it work. Along about sometime there, about 1543, and this was amazing. Now, this guy was up in what is currently Poland. Now, the church was centered down in Rome, in Italy, so they were pretty far apart. But the surprising thing is, this guy was a monk. He was a member of the church, but he was also quite a scholar, quite a thinker. And he observed that everything was sort of falling apart with the models. Things were problematic there, but he developed his own model that the sun was the center. Now, he said of the universe, all it is the center of our solar system, but that was pretty much the universe at the time. And he said, if you put it there, wow, all these other things make sense now. What Mars is doing, all this other stuff, it does make sense. However, he didn't want to buck the system because he was a good Boy Scout. You know, he was in the church. He didn't want to fight against the church. So he wrote up his observations and his explanations, but he refused to publish them. And he just tucked them away somewhere. And I can't remember the people's names here, but many scientists, many people were, this was the Enlightenment, the Renaissance, and they were thinking, these things just aren't working. There has to be another explanation. And somebody thinking that way was saying, hey, you need to go talk with this guy up in Poland. He's really put together a pretty good system. So this guy, I can't remember his name, went up and became sort of like an assistant, almost a servant of Copernicus. And he helped him organize his papers. Copernicus was getting quite old, and so he helped him he studied under him. Copernicus explained his ideas to him. He was fascinated by them. And then once Copernicus' health got really bad or he died, then this guy pulled out his work and published it and gave him the credit for it. So Copernicus didn't get in any trouble because he was already dead, but it went under his name. And oh my goodness, you talk about an uproar. I mean, it was pretty drastic. You know, the church was furious. The believers in the Ptolemaic system, whether it had any church affiliate, they were furious. Everybody was mad. You can't do this. This isn't right. We know this isn't true because we've led this our whole life. Okay? Well, but more scientists read it and said, hey, this makes sense. One of those scientists being Galileo. Now, the bad news for Galileo is he lived in Pisa, Italy, which was just not too far from Rome. Up in Poland, that was far enough away you could get away with stuff like this. Not Galileo. He was too close to Rome. Rome was ready. They were livid. Okay? But Galileo was already a very respected scientist. So they didn't feel like they could get away with murdering him, okay, or burning him at the stake or something like this. So what they did was put him under house arrest. He was found guilty of his treasonous ideas, his sedition or whatever, but they didn't want to damage him. He was too well respected as a scientist. So they put him under house arrest. And therefore he stayed there for most of the rest of his life. I think he did finally get a pardon for reprieve a little bit later, but he was past his prime, so to speak. He still did work. Now, actually, he did get free because they were so much pressure on him, they made him recant his earlier support of that. So he published the recanting of that, but then also published, said, they made me do this, and I really still believe the other. But he didn't publish that. But he kept writing. He kept supporting it. Built new telescopes. He was convinced this was true. Because, you see, he could see Jupiter, remember? He could see those 4 moons of Jupiter. He could see they went around Jupiter. He could see Jupiter was spinning. He could see the moons were spinning. And he said, hey, if they can spin, why can't we? If we spin, it makes it look like the sun is moving. It's not. We're moving. So it was all making perfect sense to him, and he wrote it up. He just didn't publish it again until after his death. And boy, I bet you they relived it again. But by this time, it was all falling apart. So the inconsistencies of the geocentric model were explained really, really well by the heliocentric. Helio means sun-centered model. This is Earth-centered model, sun-centered model. So here helps explain coral Mars, okay? Here is the sun in the middle. We're going around the sun, okay? Now, at the time that we're here, Mars is coming in over there in this direction. So it's acting sort of normal. When we move to here, Mars has moved to there. So when we move to there, Mars has moved to there. When we move to here, Mars is there. It looks like it's speeding up, just looking in the sky. And then when we move to here, Mars has backtracked on itself and come here. It really hasn't. Here's where it is. This is how it looks on the celestial sphere. Where it is when we're here, Mars is really there, so it looks like it's there. When we're here, Mars is there, looks like it's there. When we're here, Mars is there, looks like it's there. When we're here, looks like Mars is going way over there. It is golden here, it just looks there. But when we get here, Mars is directly overhead, so it looks like it's backed up. It's not. It's moving very regularly in its orbit. We're moving in our orbit. But our orbit is smaller, and we move around there faster. Mars is larger, and it moves more slowly. This is why it looks like it wiggles around in the sky. Not on a given night. You don't see that. Night after night, tracking it is not making any sense, and that's because of this. And you see a mathematician, a scientist could look at this and say, oh yeah, that makes sense. Whereas the others out there saying, this makes no sense. We have to adjust the model, No, this model works. Except it didn't work perfectly. That model, the original heliocentric model, I think probably from Copernicus, assumed the sun in the center, everything else in concentric spheres, perfect spheres around the sun. That's how they pictured things around the Earth before. Well, Kepler came along with his laws of planetary motion that further explained the heliocentric model and took some of that little bit of error that it had out. And one of the key things in Kepler's law was that we don't go around the sun in a perfectly circular orbit. We go around an elliptical orbit. Sometimes we're closer, sometimes we're further away. Okay, closer, further away. This is what introduces some of the other wobbleness, you might say, to the model. Once you get that, and that was his first law, two other laws in there, I mean, that thing fit like a charm. The trouble is, he didn't know why. All he could figure out is this model works. Okay, I think it's a music class. You want me to close that door? All right. Yeah, I think that's a music class. I'm not sure. Okay. So, he turned, I'm pretty sure of this, but it may not have been exact, but I think he turned to Isaac Newton and said, could you come up with any reason this happens this way? This model fits, but it's all empirical. I don't know why it works, okay? Can you help out? And that's one of the reasons Newton came up with his three laws of motion, because he had to give the why for things like Kepler's laws and other laws to make sure they had a basis. Excuse me. Oh, man. You have a couple figures in your text that look kind of like this one, but they probably describe things a little bit better. For instance, your figure 1522 shows what things look like if you assume the Earth was the center of the universe. Okay? And Venus would have been going crazy in there. Then The captioning on figure 1523, I think, leaves a little to be desired. It shows Venus way too close to the sun compared to Earth, and the sun out there. And the captioning makes, okay, the A part that's at the top of the page, which is almost like, well, it's not quite the same, but, you know, figure 1522 has the Earth at the center, and then Venus going around it, but wobbling badly, and then the sun beyond Venus, okay? The U.S. customary and the, sorry, having trouble breathing. The figure 1523 has the Copernican model, and it has the sun in the center, then Venus, and then Earth beyond the sun. So it's kind of like they exchange who's the center and where's sun. Venus stayed pretty much where it is, but they flip-flop, and therefore the path is almost the same, but now you can explain it, you know. Before, it was inexplicable, okay? But now it's more so. Now, what I was getting at, the captioning here is bizarre, kind of. The Ptolemaic system, that's over on figure 1522, explanation of Venus as a morning star and an evening star, that's just what it stated there, okay, on the A part. Then the B part says, I'm sorry, on the left-hand part is Ptolemaic system, explanation of Venus as a morning star and evening star, okay? The A part above, the it says Ptolemaic system. I think they got these backwards. I think this is Ptolemaic. This is heliocentric. But they have A being heliocentric. I think that's wrong. As the morning and evening star, and then B, the heliocentric explanation of Venus as the morning and evening star. That's down here, showing Earth, same picture with Venus. And remembering completely, it's just called morning and evening star. It's not a star at all. Okay, now on page 400, two figures. Oh, and here's the one that's in your book as well. Okay, the other two preceded this one. Okay, here is a hugely distorted explanation of Kepler's first and second laws. First law is in 1525. Now this, again, is hugely distorted. They show the sun on one of the foci of an ellipse, and then the planet going around it. There's not any planet I know of that has that much of an elliptical orbit. They're all closer to being circular, they're just slightly elliptical. Okay? But with that kind of a scale, which is not right at all, they then showed, remember I said earlier, that an object, especially like the comets and things, they move near the sun, they really pick up speed. They're quite fast. When they're further out, they slow down. Okay, and then they pick up again. They're fast and slow down. Okay? Kepler's second law says the area swept out by the radius of the object from the center of the Earth here, that gives you the same same area as this one when it's way, way far away and moving much more slowly. Okay? So the same area over the equal time periods are mapped out. This is one of those things that Kepler discovered, but he couldn't explain why it was the case. Now the third law is given at the bottom of page 400. It's a little more complicated, but it's really okay. States that the square of the period of the planet's orbit is proportional to the cube of that planet's simulated axis. Okay? All right. So, now, you might ask yourself, how in the world, I ask myself, how in the world did Kepler even come up with the idea of an ellipse? And then what's more, that equal sectors of that, that requires a lot of pretty deep observational analysis and understanding of geometry big time. Okay? Now, when he came up with this one, that's in one sense a little harder, but in another sense, I think they had logarithms back then. And if he had been doing it using logarithms, this is a pretty incredible little table here. If you plot the distance that the object is from the Earth in astronomical units, as Earth's radius, average radius being 1. Mars is much less, Venus is more than Mars is close. And you see, look at how the planets stack up there. My word, so regularly. Oh, this is a log scale here, also the period of the planet there. Who would have thought to compare those things? The period of the planet here, but also put that on a log scale. That takes away the exponents, basically, and makes them multiply. So now there are different slopes. Look at that. Mars, Venus, Earth, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. They're almost equally spaced, except for what? A big gap in the middle. What would fill that gap? If the asteroid belt had become a planet, that would fit in there just about perfectly. Amazing. Amazing. Okay? And guess what? The line keeps on going. There's plenty of room out there for maybe another planet. That would be, whereas Neptune is well more than 100, maybe 110 light years from, astronomical units from the Sun. That next planet out there, if you spaced along there well, that would be, looks like on the neighborhood of 120 to 140 light years away. So, wow. Not light years, astronomical units away. So no wonder we can't see it. It's so far out there, the reflection would hardly register. So this is a bit bizarre. All right, now there's some examples given here, and if you look at them, you see their formulas are really fairly hairy. These are things we did. Justin and Lauren, okay, in Physical Science 1. but the rest of you haven't had that. Those formulas are a bit on the hairy side. So anyway, you can read through these and see what they come up with, and it's pretty interesting stuff. And just basing it on what is the using the formulas we had from the front part of the book, you can estimate things like the mass of the sun without ever putting it on a scale, okay? With any other thing, you can estimate that. Now, there are some people behind the science, one person who's mentioned here, and remember, this could be where you get your ideas for your paper, this can't be your source for your paper, okay? And this is Gerard Peter, and I wish they put a pronunciation of his name. It's either Piper or I've heard it pronounced Peeper. I don't know which is correct. If either, maybe neither one of them. He was actually born in the Netherlands, Dutch born, but he immigrated to the U.S. And became what they call a natural citizen. I hate to say this, but it's really true. Back then, in today's terms, all these people would be considered illegal aliens. But you see, back then, we had a completely different mindset. Yeah, come on over, you know. Great minds, hardworking people, you know, come on here. Statue of Liberty has the thing on it. You know, send us your poor, send us your, we want them. We need, things have changed. But he came over and went to several places. I think got his education here. No, he completed his education in his own country, immigrated here, and became a naturalized U.S. citizen. He joined the staff of, moved around some, but his work on the origin of the planets stemmed from theoretical discrepancies that arose from new 20th century hypotheses on galactic evolution. Blah, blah, blah. So if you read through this, he was more than just that comet belt out there. They named it after him. He did work in many, many, many areas of astronomy. Okay? All right. There's just an enormous amount of information here. Again, this can't be your source, but it can point you to somewhere else. All right. Now, I say this at the end of every chapter. Nothing replaces reading the text. I'll make a confession to you. First time I taught physical science, which was probably 10 or 15 years ago, maybe not quite 15, when we first, shortly after we merged, we started teaching physical science rather than just physics. And the first thing in this course is astronomy. I have never had a pure astronomy course in my life. So here I was having to teach 3 chapters on astronomy. And literally I went home every evening and read as much as I could of every one of those chapters before I had to teach it. So I was reading through portions of it 3 and 4 times before I felt comfortable enough to teach it, because it would be saying one thing here and it sounded like it was contradicting it here. But then I realized, no, that's a slightly different term. So it took me several readings for this to make sense. And you're probably not as slow as I am, but you know, it probably would help if you read the text. The summary here is shorter than most of the chapter summaries, but it has the highlighted, important features highlighted and, sort of like Reader's Digest, condensed. The key terms is about normal, I think, and they are listed alphabetically, but they are given by page number where they're located. But the very best thing in my mind to study for the test is they're applying the concepts. Multiple choice questions. Most of your test questions are usually going to be multiple choice. There may be a few fill in the blank. Very few calculation. Just fill in the blank. So these are not the same questions you'll see on your test, but if you know the material for this, you know most of the material you'll need for the test. Now, there's only 41 of those, which is a few fewer than normal, but it's still a good number. Your test won't be more than 20, okay, so this is more than twice as many. But if you know these concepts, and they have the answers given, so if you go through and work these out, check your answers. If you don't get it right, go back into the book and see if you can figure out where you got it wrong. If you can't, bring it to class. We'll go over it. I had found some wrong answers in the earlier edition. So far, I haven't found any of these, but I haven't gone through them all. I'll wait till students to ask me questions about them. But sometimes the questions are little bitty twists of the wording that's not really what they're asking for. They're asking this, and then the question makes sense. Now, questions for thought, 19 in this chapter. That's probably a few more than normal. 6 for further analysis. That's about like normal. There's an interesting little conversation or invitation to inquiry, and that deals, I think, with how long it would take to talk to something even as close as Venus away. That would be a very long conversation because it takes a finite amount of time. The parallel exercises, they're supposed to have, for the Group A, your answers in the back. When I've looked at the small books, I can't find them. I specifically asked them to put that in. The first customized printing they did for me, they did not do that. So I specifically asked for it this time. They said yes, but I haven't found it yet. But if you find it, let me know. Any questions on Chapter 15? So again, it's about 1:10 now. Yes?
I have a question. It's not related to Chapter 15, but I have doctor's appointments, so I'm not going to be able to stay for the lab. I was wondering if I could take it with me and do it while I'm waiting and then bring it back.
Okay, certainly. And then anything that you can't figure out on your own, if you'll listen, I'll record the lab too. Now, as you saw before, I won't always be standing real close to the computer, so it might be I'll fade in and out some, but I think you'll be able to follow a lot of it because we'll do it en masse in class today. Okay, so get it before you leave. When do you have to leave? Right now?
In just a minute.
Okay.
I'll be there at 1:45.
Okay, we'll pick it up on your way out. Okay? So where we're going to start now is Chapter 16, which is Earth in Space, on page 407. Okay? So let me get out of this and get to the next chapter. Okay, Chapter 16. Now this is our last chapter in the astronomy section. After this we go to earth science. And that builds on what we've been doing here, but it's sort of a different focus. Okay, it's focusing right on us. Okay, there it is. All right, here it comes. Okay, Earth and space. So we started with the universe, that was Chapter 14. We went to the solar system pretty much, that was Chapter 15. Now we're looking at Earth and our only natural satellite, the moon. So we're going to look also at the moon in this one. In fact, the lab for this one is going to be focused mostly on the moon. Okay? So here's the core concept, which you found on page 407. Goodness, my eyes hurt. The way the Earth moves in space is used to define time, to describe location on the surface, and causes other recurrent phenomena such as the seasons. And we'll talk about this. I think we've mentioned many of these in the earlier chapters. This one we're going to focus on that. Okay? And this is a pretty neat little picture here. It's not a great picture. It's still just an artist's rendition, but it's that's about the best we can do. And my guess is this is supposed to be Mercury. Okay, that's pretty closely Earth. Here's Venus. Now the Venus looks outside, but it's not. It's just the perspective of it. Mars is over on the other side. That's Mars. This is probably Jupiter. Okay, Saturn. And you'll never see Uranus look like that. But this seems to be the moon. This seems to be you're on the moon looking at these others. Now, certainly the scales are wrong. Venus is never close enough that it looks that big. None of these are. These are barely points of light, but it's just another way to try to get a perspective of these things. Not anywhere close to right perspective. Okay? So let's start with the shape and the size of the Earth. Okay? We're not a perfect sphere. We're a very close to, and what they call an oblate spheroid. Now, what does that mean? We're slightly pear-shaped, a little bit bigger on the bottom half and thinner on the top half. Okay? We're slightly pear-shaped. That's sort of the oblate spheroid. Spheroid means like a sphere, but not quite as a perfect sphere. Now, this part makes no sense to me. It says there's a lump in the Pacific Ocean. Seems like if there was a lump in the Pacific Ocean, it would smooth itself out, doesn't it? I think what they mean there, Pacific Ocean bulges a little bit. It's not a lump in the ocean. The Pacific Ocean bulges. And there's a little bit of a depression in the Indian Ocean. It seems like it was filling with water, but that's not really what they mean. That's the place where we're a little thinner than we should be. A little thicker in the Pacific, a little thinner around the Indian Ocean. Now, the elevations and depressions of these deviations, the differences between those, okay, is less than 85 meters. Now, anyone want to make a guess of what 85 meters is? Picture a football field. You go from probably the 10-yard line to the goal line, the next other goal line. What's that? Right, okay. But what that is, you've seen a football field before. It's not quite a full football field length. Okay? That's the difference between that bulge in the Pacific and depression in the Indian Ocean. It's not much. You can stand the football field and cover that difference. So it's not very far off, but it's not exact. Okay? Now, this makes it look worse than it is because part of this is in the dark. The sun is over here. This isn't a full Earth, but it's pretty close to it. We're very close to being spherical. And you see here, this is a picture from the spacecraft. This is the Baja Peninsula, south of California. That's in Mexico, actually. This is the Gulf of California up here. Basically, this is Mexico, this is the U.S. And most of this is water, okay? I think Alaska is somewhere up in here, but it's hard to see. This is a little bit of South America down here. There's Central America. There's a storm brewing over here. But that's Earth, okay? But don't think we're that far out of alignment. It's just that this is the nighttime over here. You just can't see that part of the planet. Okay. Now, this is an exaggerated example. The dotted line here, dotted curve here, would be a perfect sphere. The green ball here is what they call the oblate spheroid. Now, part of this is that our vertical axis is shorter than our horizontal axis. And again, we're thicker in the middle and thinner at the top. Now, that is not what this is talking about, because you see this is a lot more than that. The difference here, and it's not much here either, if you consider 12,714 from 12,756. So that's a difference of only 42 kilometers. 42 kilometers, that's probably here to Birmingham. Okay? So the difference out of 12,000, almost 13,000 kilometers, or close to 8,000 miles, it's the difference of 26 miles. So that's a very, very, very small difference between our biggest dimension horizontally and a shorter dimension vertically. Very, very close to a sphere, but not quite. Now, let's consider the motions of the Earth. And by the way, there's another picture here, which I don't know if you've gone to the website yet, to the Blackboard yet, and looked at space objects in perspective. And this really would have been a better picture in the last chapter. This is artist's concept of the relative size and order of the 8 planets in the solar system, not to scale, okay? And certainly not, they're never in this close of proximity or anything else. There's Mercury, Venus, Earth. Now, Earth is actually larger than Venus because it's behind it. It looks a little smaller. Mars. Now, Mars is really a bit bigger than Mercury because Mercury is closer. But those are the 4, what do we call those 4 inner planets? Special name. The what? They're just terrestrial, not extraterrestrial. Just terrestrial planets, also called the rocky planets. Okay? And you see the backdrop for them? What's that? Hint? Great red spot. Jupiter! That's how big Jupiter is compared to Earth and the other 4. It's a monster. Saturn is a big planet too. Only thing is, Saturn is not very dense. It will float in water if you have enough water. Okay?
So it sounded like the picture.
What's that?
So it sounded like the picture of the thing was right here.
My hearing said
I
that.
said it sounded like the picture right there.
Said it one more time.
It sounded like the picture.
Oh, okay. Yeah, this is the artist rendition looking at satellite pictures. The artist is drawing the 3 fairly close. See that great red spot is bigger than Earth is. Okay, yeah, that's a monster. Okay, Saturn is huge. Uranus and Neptune are huge too, especially compared to the closer ones. Okay, terrestrial planets. Okay. And then the fact that we, the Earth, have a moon that almost as big as the biggest ones of Jupiter and Saturn. That's pretty incredible that our moon is that big. And we'll talk about that a little bit later. Okay, and there's also a picture of the ecliptic, which if you remember from the last lab, that's the path that the sun takes around the Earth, because the planets are all fairly close to, they're in the same plane of the of that path. They all would be located really close to that ecliptic. And you see Mercury, but you'll never see Mercury that clear. Jupiter, right on it. Regulus, I don't know why it's so close. Mars is right on it. Spica is a star. Saturn. Why don't they show Venus? That's the one I'd like to see, but maybe it wasn't in sight at that time. All right. So let's now look at the motions of the Earth. This is 16.2. Okay? There's bunches of motions that the Earth has. 3 of these motions are completely independent of the motions of the Sun and the galaxy. So whether the Sun or the galaxy were there, or whether they're moving or whatever, these 3 would still be happening. Number 1, once a year, we move all the way around the Sun. That's what makes a year a year. It's the yearly revolution about the sun. But while we're revolving, we're spinning like crazy. Okay? So it takes 365 and a quarter days for it to make one trip around the sun. It takes us 24 hours to make one spin. So that's our daily rotation about our own axis. Okay? Now, here's another thing that's a bit bizarre. The Earth wobbles a little bit. Have you ever, I don't think anyone plays with it anymore, a top? You ever see anyone play with a top? Maybe old videos or something like that. Yeah, it's spinning a top, okay? When you spin it real fast, it stands almost perfectly straight. But you see, it almost always has a little bit of a movement with it, of its axis. That's called precession, okay? That's that clockwise wobble of the rotation axis. Now that's very, very, very slow, okay? You'll never notice it. It's only over long periods of time do you see effects of that, okay? So these are the three motions independent of the sun and the galaxy, okay? Now let's look at all of them. This is motion of Earth through space. 7 very conspicuous motions. One of these we just mentioned, the daily rotation of the Earth, and that's about close to 1,700 kilometers per hour, which would be about 1,000 or 900 to 1,000 miles per hour. That's how rapidly we're spinning on the equator, the fastest thing. You never sense that because we're on the Earth. It's such a big thing. We have a monthly rotation about the Earth-Moon center of mass. Now, we'll talk about this later, but remember, our moon is pretty good size compared to us. Nowhere close to the same, but closer than any other planet. And it's not that the moon moves around the Earth, it's they move around the center of axis. The Earth actually moves when the moon moves, just not nearly as far, because it's much more massive. Okay? Number 3, the yearly rotation about the sun. We talked about that. And that's going 106,000 kilometers per hour, which would be about 60,000 miles an hour. Us going around the sun. Of course, we don't sense that either. And then there's the orbit of the solar system about the center of the Milky Way. Remember when we had the picture of the Milky Way, there was that galactic nucleus in the middle, and then the spirals that came out around. We were way down there. This whole thing is spinning around the axis of the around that nucleus, and that's going about 370 kilometers per hour, which would be 200,000 miles an hour to 240,000 miles an hour. Whoa, that is really flying. Okay? Now we also have an orbital motion within the sun's local star group. There's a group of stars that the sun is part of, and we have an orbital motion within that group. I'm not sure why they said that one before this one, that we do, except it's so much faster, and that's going about 1 million kilometers per hour, which is about approximately 600,000 miles an hour. Okay? And then you have the motion of the Milky Way galaxy relative to other galaxies out there. And remember, we talked about this before, we're moving further apart all the time. That's another 580,000 kilometers per hour, which would be about 350,000 miles an hour. Okay, those were the big ones, conspicuous motions, though we don't sense any of them. And here are some of the minor motions. Changes in the shape and size of the Earth's orbit. Okay? Now, if you remember this, we said it earlier, the planets don't move in circular paths, they move in slightly elliptical paths. So we're going around the sun, and sometimes we're going faster, sometimes we're going slower, sometimes we're big radius, sometimes small radius. It's not much of a change, just a little bit of a change. These are very, very minor changes. Changes in the tilt of the Earth's axis, that's that precession we were talking about. And unfortunately, as we get older, we get slower, don't we? The Earth's rotational axis is slowing slightly. Again, very, very minor. Nothing you will ever notice in your lifetime. It may be that one time, thousands or tens of thousands or 100,000 years ago, we may have been only had 23 hours in a day, okay? Because the way we measure hours, because we're spending a little bit faster then. But it's nothing that you'll ever notice in a lifetime, any slowing. It's that minor. Okay? Does anyone need this up here a little longer? Okay, yeah. Take your time. This is a lot on the slide. So I tried to yak about it. So you can get it down. This has been one busy week for me. Goodness gracious. So running out of steam. After we had class last time, that was voting day. I hope y'all voted. If you didn't vote, be sure you vote in the runoffs, because there are some runoffs coming up. But we had been helping with one of the campaigns with one of our local representatives for the state house seat that in the district we are. And so we were invited to his, what they call a watch party. And he was way ahead of the other two people in his race. But it was only like 51, 52, 53% to 25, 28%, something like this. So he was way more, but he didn't have, it wound up right at the end, he slipped down to 49%. So he doesn't win, even though they only had 26 or 27%. He's still there in a runoff. But we were waiting, trying to see if he was going to win. It was so close, and then did it. So I lost sleep that night and never caught up since. So, okay, y'all got this? So I'm struggling today. Okay, let's move more of Earth's motion in space. The overall picture from space, now get this. We're spinning, we're moving around the sun is moving around the star group is moving around the galaxy, and the galaxy is moving with respect to other galaxies. Okay? So on the simplest scale, we seem to be moving at a helix. We're going around the sun, but the sun's moving here, so we're doing this, sort of. Because the sun's moving around this galaxy. Okay? At incredibly fast speeds, okay? But we don't sense those. Now, viewed from Earth, you see the ecliptic plane, that's the plane of the Earth's orbit around the sun, which is sort of like the plane that it looks like the sun is going when it's moving around the Earth. Of course, it's not, we're moving back. And that's because of our tilt. Okay? Now, can't quite get this exactly right. So I have to be outside here. But if Christy is the sun again, you don't want to be the sun. Okay. All right. Right now, relative to our tilt, you're awfully close to here. Okay. So that's where you are. Okay. Because of this, when we get over here, you're there. When you get over here, you're down here. Okay? That's where you are because we're tilted this way. That plane, if you cut slices of the Earth to represent that, that would be the ecliptic. Okay? So that accounts for that. The ecliptic plane is the plane of the Earth's orbit about the sun, and because we're tilted, that doesn't map along the equator. It's slightly tilted. In fact, slightly, how much tilted? Y'all remember from the first lab? What's the tilt? 23.5 degrees. Perfect. Okay? The planets move in a narrow band about the ecliptic plane. In other words, the solar system is pretty flat. Okay? Now let's move the Earth in a little bit. Mercury would be there going around. Venus would be there going around. Mars is there. We're all in almost a pancake. Or, probably better, a fried egg. Okay? With the sun as the center, we're all the white, going around there. Okay? The solar system is relatively flat. Even the Kuiper belt, or whatever you say, is pretty flat. It's the Oort cloud that is not flat. Okay? The sun moves along the ecliptic across the background stars. Now think about this way. Okay. Here's the sun again, right? Okay. Here we are. Now, only this half of this Earth is in daylight now. That's the only thing. This half is the dark. So this half is seeing stars over here. Now remember, the stars are fixed. They don't move. Okay? So we see these stars really well at this time of year. But when we move here, these stars look like they're moving. Well, they're still there. We're just moving here. And then when we get over here, and those stars are there, the sun's there. It bleeds them out. We'll never see those stars in the wintertime. But we'll see a whole new group of stars that we get to see in the summertime. So the stars, the sun moves along the ecliptic across the background stars. So it looks like the sun is moving in different patterns of stars. Okay? I was looking at it this way. I'll bring my globe. The sun, when the sunrise over here, that right before the sun rises, we'll see the stars that are right there. When we move here, right before the sun rises, we'll see the stars that are right there. And so you see, we see different groups of stars. And guess what that's based on? I mean, what we base on that. Can you have you read the horoscope? What do you call those? The what? Oh, there's a name for it. I can't think of what it's called now. But anyway, astrological, whatever that is called. And so the sun is rising in Leo, or it's rising in Gemini, Capricorn, Sagittarius. What do you call those?
Zodiac.
What's that?
Zodiac.
Zodiac, yeah, the zodiac signs. Those are the constellations that the sun is coming up in, or something like that. So it changes as you go through the year, and that's what all that's about. It's only because we're spinning. I mean, we're moving around the sun, and we're tilted. Okay. So that's the zodiac sign. Okay. Now, here is this helix, because we're moving around the sun, but the sun is moving in space too around the center of the galaxy. Then we're doing this as we do. We're like a corkscrew, kind of, just spinning around and around and around and around. Okay. Now, the revolution, which I've just been describing, the Earth's movement around the sun is a time. Oh, yeah, it's past time. Y'all didn't stop me, did you?
I was going to say that.
Oh, okay. We'll have to stop there, and this is revolution. Goodness gracious. Rotation. Where is revolution? I think this is what they call orbit, so I'll leave that alone. Okay, let me pause and go back to current slide. Again, I won't need it right now, but let's get started. All right, we've got most people back. And 2, I've got to call roll again, so remind me of that. We do have the recorder on, so that's good. Okay. Now, the last experiment we did, or the last lab we did, it says there's a prerequisite for this one. So we're going to be doing a little bit of the same type of stuff, but moving on from there. Okay? Now, if you are tracing the motion of the sun, facing pretty much due south, it rises in the east over here, right? Yeah. Rises in the east over here. Right now it's rising a little bit north of east. We talked about that last time. And moving upward, and it reaches the highest point in the sky that it'll ever get today, and then it starts going down, and it'll set a little bit north of west, okay? Following that kind of a pattern, okay? Now, that highest point it gets in the sky is right along our meridian. Where it crosses the meridian, that's the highest part it'll be, okay? Now, technically, that highest point, when it reaches the highest point, that's our real noon. That may not be noon by the clock, but that would be our noon. When it's the highest point it'll ever get in the sky before it starts coming down again, that's noon, okay? Fundamental reference in the measure of time. Now, if you go from one noon today to that same highest point in the sky tomorrow, that's one solar day, based on the sun. One solar day. It's approximately 24 hours, but not always exactly 24 hours, okay? We set our clocks according to 24-hour days, but that will some days be a little bit shorter, a little bit longer, but that's technically a solar day, okay? Then they break days into smaller units, hours, minutes, seconds, okay, and so on. Now, the first ones to break down days like that were the Romans. They had a really strange way of doing it. Just like the Roman numerals were really strange numerals, right? So their days were. They decided, and by the way, in the morning, what time do we say that is? It's 10 o'clock in the morning, we say it's 10 a.m. That stands for anti-meridian, like anti-meridian. That means before it reaches the meridian, a.m. Remember, that's the morning hours. And after the meridian, when it's on its way down, that's post-meridian, which is p.m. So that's where that comes from, okay? And those are Latin words, and that means after the meridian. Now, the Romans did something strange. They said the number of daylight hours is 12, whether it's winter or summer. So in the summertime, an hour was much longer than it was in the wintertime, because there had to be 12 hours of daylight, okay? So that made for strange. They couldn't build clocks that way, okay? That was really bizarre, okay? So clockmakers had trouble then. I think the Romans were the first to come up with the idea of the sundial. That's the thing that faces probably due south, okay? And you set it up so that the shadow then tracks along, and they divided that into 12 equal increments, and that told them about, let's say, the shadow would point out about what time of day it was. When there was a bright sun. When there was a bright sun, you couldn't tell what time it was, okay? So they did a lot of things. Now, that sundial was used probably by more cultures than just the Romans, but there is another kind of sundial, you might say, and we're going to talk about that a little bit later in this lamp. Okay? Different type of a sundial. But let's move on to page 370. The solar and the sidereal day. If you were a stargazer and you didn't like being up in the day to see when it crosses your meridian, and when noon to noon, that's a solar day. If you're a night owl and you just were up at night and you say, well, I'm going to see when a certain star crosses my meridian, okay? And I'll count my days from that. If you did that, that would be a sidereal day based on the stars, and it's different from the solar day. Just by a little bit. Not much, but by a little bit. And here's why. If you'll go to, you need to read it all. I'm trying to get through it quickly so we can do it in 2 hours. We got a little bit left. The sun moves 360 degrees, okay? Sun moves 360 degrees around the ecliptic, all the way around, in 365 days, right? So that's almost a degree a day, right? 1 degree per day, okay? Now, remember, if I'm here looking at the sun, maximum height in the sky, and then later at night I'm looking at some star that crosses that maximum height in the sky, that star is always there. The next day, because I'm going around the sun's moving slightly. See, if I'm here one day, and then I move to here, the star, you have moved a little bit, okay? You look like you have. You stayed where you were, but I moved. And that's about 1 degree east of where it was the day before. So calculate how long you will have to wait after, okay, you have to turn one more page. So let's say we're doing it on spring equinox, vernal equinox, when the sun and the local celestial meridian, that's the highest point of the day, when that crosses the ecliptic, all three of those are in one little location there, okay? The next day, because the sun has moved slightly, gone a little bit higher in the sky, we haven't reached the noonday yet. But that's where we were the day before. It's moved about 1 degree more. Now, the question is, back that up, 1 degree more. Calculate how long you would have to wait after that situation so the sun is on the meridian again, okay? And it said express your answer in minutes. That's time minutes. So we already said that the sun moved approximately 1 degree a day, right? But a day is how many hours? Okay. And it said express your answer in minutes. Okay. So that would be 1 degree in how many is that? 24 hours times 60? That would be 1,440 minutes. Okay? Now, I'm sorry. Okay. Oh, good. Here is Jordan, right? Barely made it into the class time. Ooh, 3 minutes. Okay. In fact, we should be on break right now. No, we'll count you here. Okay. Now, That's not quite what I was looking for, though. Oh, you need a lap. Sorry, that's the paper roll. First question, by the way. We talked about the other stuff, but we're on the first question. So, what we have to do is 1 degree here. Let's say that is 1 degree. 1 degree. Okay, that it's moved. And there's how many degrees around the circle? Okay, 1 out of 360. Okay, 1 degree out of 360. And that would be equivalent to how many minutes I'm sorry? Say that again. Okay. Yeah. Okay. What we're talking is 1 spin of the axis. Okay. This isn't 360. 1 spin of the axis. And that takes 24 hours. Okay. Is that what you're getting at? Okay. That takes 24 hours. Okay. So what we're asking for, so how long does that take to move the 1 degree? If it takes 360 degrees, that's a spin, in 24 hours, how long is 1 degree? So what you would do there is divide 360 into 24 hours. But let's do it into minutes, and that minutes would be 1440 minutes. So if you got your calculator, divide 1440 divided by 360. What's that? Four. That would be right at 4 minutes. So that's how long it takes between one day and the next day. So the difference between a sidereal day and a solar day is about 4 minutes longer. Not very much, just a little bit. 4 minutes longer. Okay? Now, this next question is bizarre. It's referring to the zodiac signs, which is on the next page. And if you read the question, it says figure 48.3 depicts the sun's apparent motion along the ecliptic where the zodiacal constellations are found. So there we see the Earth over here, the sun there, and that the sun we say is in Leo. Okay? As the Earth orbits the sun, the line of sight from the sun toward the background stars also moves. So when we move over here, then we'll be in Virgo. When we move over there, the sun will be in Libra. Okay? Blah, blah, blah. Okay? For example, the diagram shows the sun in Leo. A month later, the Earth will have moved enough so Virgo lies in the sun. Okay? Does anyone see a question there? No. Okay? They have a number 2. They have an explanation, but they forget to ask a question. So that was a freebie. Don't mess with it. Okay? It just showed you this. But then there was no question asked. I can't imagine what they're getting for it, but it's not. So now we're moving to Part A. And Part A is dealing with the analemma. Now the funny thing is, this corresponds to Chapter 15, but the analemma isn't mentioned in the book until Chapter 16. So we'll be talking about that next time when we do, I think we'll get that far along. So the analemma, by the way, that name means sundial. That's the Latin name for sundial. So, but this isn't quite the same sundial you think of as casting a shadow. This is slightly different. But again, you're measuring the movement of the sun. Okay? Now, what the analemma is, now let me try to give you my best guess at how this is. If we were going to try to do this properly, we'd have to cut down a couple of trees here. Okay? We're not going to do that. Okay? And then what we would do is cover over both of those windows with black plastic as completely as possible. And wherever the best location would be, we put a little bitty hole in that black plastic. Okay? And then at noon every day, true noon, when the sun reaches the highest point in the sky, we would mark on the floor here exactly where the sun was. And the sun crossed that highest point, we'd make the little dot where it is. And as the year goes on, we would make dots that go around like this, around like this, around like that, around like this, and back like this again. We would form what they're showing next. I don't think I need the slides anymore, so I'll leave it up there now. Okay. And that would form this. This is called the analemma. Okay? The highest the sun is in the sky is around June 21st, and that would be when the analemma would help it. It would actually be that way. That would be the point of the floor there. The lowest it is in the sky, the longest shadow it would have would be down here around December 25th. Okay? And then where the sun where the shadow would be as close to zero as it ever is. On the equator, where the shadow would be at zero, that would be on March 21st, and you see that's over here on the right, and on September 21st, that's on the left. So this is summer solstice, winter solstice, we talked about these before, vernal equinox, equal day, equal night, autumnal equinox, equal day, equal night, where it crosses the equator. Now, let's talk a little bit about this. The vertical scale is your declination of the sun. Okay? And we know the sun is what on June 21st? What's its declination? Second? Yeah, but what is its declination? 23.5 degrees. There it is. Just about 23.5 degrees. See, 23 degrees is right there, and that's about half a degree in between 23 and 24. And what is it on December 21st? 23.5 degrees south, and there it is, way down there. What is the declination on March 21st? 0. September 21st? 0. So every day of the year has a declination. Okay? Now, the top scale, the horizontal scale, is the time in minutes either before or after that it's either early or late, okay, that noon is. And we'll see how to use this later. So that's the analemma, okay? Some of the old globes, this one doesn't have it. Somewhere out in the Pacific Ocean where there weren't many things, they'd have the picture of the analemma, which of course would go up to the Tropic of Capricorn, Tropic of Cancer down to the Tropic of Capricorn, and your figure 8 would be in here, okay? Just like this, right between those two continents, okay? That's where the sun would be directly overhead at each of those days of those bands. All right, there's a lot of verbiage here. The spin axis of the Earth on page 375 is tilted, inclined at how much? 23.5 degrees, okay? We've talked about that many times over. The meridians of the right ascension are more closely spaced at declinations plus or minus 23 and a half than at the equator, because the spinning here, it takes there's less difference between this many degrees here than there is that less distance, because the Earth is getting bigger toward the equator, smaller toward the poles. Okay. Now, here's the other. That is the reason, the fact that we're tilted, that's the reason the analemma, we go up and down on the analemma. But what the other thing is, why we go further apart and closer together, is because sometimes we're closer to the sun. Actually, this is surprising. We'll see this later in this chapter. We're closest to the sun on January 4th or so. Okay? And that's why the slope is so shallow here, is because it's not changing very much. But on days when we're further from the sun, it's around July 1st, sometime. So that's why you're thicker down here and thinner up here. It's not a perfect date. That age, that's why. Okay? All right. So one further influence in the shape of the analemma arises because of the elliptical orbit of the Earth around the sun. The planet moves fastest near it is perihelion, and here it actually tells. Okay, I thought it's in the book, but it's here too. Point nearest the sun, source of the aphelion, which is when it's furthest from the sun. The Earth reaches the perihelion on January 3rd, the aphelion on July 7th. Okay? Now, that's really good news for us, if you think about it. Because in the middle of winter, we're actually a little closer to the sun, January the 3rd. And in the hottest part of summer, we're actually a little bit further away from the sun. Okay? But, on the other hand, these poor people down south, like in Australia, okay, they're actually closest to the sun when they're tilted toward the sun. And they're farthest away from the sun when they are tilted away from the sun. So it seems like to me, I've never read any data like this. There should be a little bit measurable more extremes of temperatures there than we have here. I don't know if that's the case. There are other factors involved, but it seemed like just from proximity to the sun, that would be the case. Okay? So the motion along the sun is faster than average during the winter months, slower than average during the summer months. So how far they vary. So, question number 3, finally, on page 376. Briefly describe the effect on the shape of the analemma if the ecliptic equator angle were to increase. In other words, if we would tilt a little bit more than what we're tilted now, what would that do to the shape of the analemma? What would happen then? What does it go up to now? 23.5 degrees. So what if it went to 25? It would be stretched out further. Okay, yeah. The analemma would be stretched out further. A little bit, depending on how much that would be. So there's your answer to number 3. Okay? Now, it says, take from the instructor the latitude of your location and fill it in below. I've given it to you before. I'll give it to you again. Read it right off the atlas. Bessemer, Alabama, right where we're sitting now, is very close to 33 degrees, 23 minutes, and 45 seconds north. We're in the northern hemisphere, so it's north. That's 33 degrees, 23 minutes, 45 seconds north. Okay? That's our latitude of our location, right where we are. Now, what we have to do with that is determine the altitude over the southern horizon of the intersection of the celestial equator and the local celestial meridian. So let's go back to our picture like this. Okay, here's a globe down here, and here we are standing here in Bessemer, Alabama. Okay, hot day. Okay, our latitude here, this is the equator here. Our latitude here is 33 degrees, 23 minutes, 45 seconds. Okay? Here's our horizon, northern horizon, southern horizon. Here is the celestial, our local meridian. This we call our zenith. Okay? Now, if that's the case, our celestial equator is about like this. I can't draw straight lines very well. This is our celestial equator, is 33 degrees, 23 minutes, 45 seconds below us. Okay? Okay? That would correspond there. Here's the celestial equator. Now, the question is, okay, let's lost the question. There's the question. Okay. Determine the altitude over the southern horizon of the intersection of the celestial equator and the local celestial meridian. That means at noon. Okay? What we've got to determine is what this angle is here. What angle is that? How do we determine it? We did it before. Anyone remember? Say again? This angle here is 90 degrees. So rather than writing 90, I'm going to write it as 89 degrees, 59 minutes, and 60 seconds. Because 60 seconds is a minute, and that would make it 60 minutes. 60 minutes is a degree, that would make it 90 degrees. Okay? Subtract from that 33 degrees, 23 minutes, and 45 seconds. Okay? And what would that give you? 56 degrees, a little louder, 36 minutes, 15 seconds. Okay? That's what this is. 56 degrees, 36 minutes, 15 seconds. Okay? But where is the sun? Okay? Determine the altitude over the southern horizon of the intersection of the celestial equator and the celestial meridian. Okay, that's what we just did. So that's going to be that. So the blank that's underneath between 4 and 5, that's where you put that. 56 degrees, 36 minutes, 15 seconds. Now, what we need to do, we're first going to do this, all 4 of these below here at where we are, at our location. So we're going to leave this on the map here. And what we have to do now is on February the 15th, determine what the declination of the sun is. How in the world are we going to do that? Go to the analemma. The analemma has that. Okay? And what we have to do is figure out February 15th. Where is February 15th?
13.
Okay. February 15th right there. And it is 13 degrees south. the declination of the sun is 13 degrees south. Okay? So that's what you fill in on the table. Declination of the sun, 13 degrees south. Now the noon altitude of the sun at our location, what you have to do is subtract their celestial equator. So we're 13 degrees south of that. So here's the sun on 15 February. So what we got to do is subtract that 13 degrees from, you see, 13 degrees subtracted from the 56. So subtract 13 degrees from that, and what does that give you? 46 degrees, 36 minutes, 15 seconds. 43, I can't read my writing. 43 degrees, 36 minutes. I was going jumping through the 6 already. Okay, so that's what you fill in on noon altitude of your sun on February the 15th. Okay, let's go to June 21st. And you shouldn't take too much time to figure out what the declination of the sun is on June 21st. Any ideas? Second? No, I don't think so. June 21st is way up here. February the 15th is way down here. I don't think it'll be the same. It's what? 23.5 degrees. You're absolutely right. So the declination of the sun on June 21st is 23.5 degrees north. And from the analemma you see that, but you should know it anyway. So where is it relative to us then? We go up here another, I don't have it by scale, 23 degrees 30 minutes. 23.5 degrees. So what do we do with that? Not subtracting. You add it to the 56. So take the 56, 36, 15, and add to that 23 degrees 30 minutes. Okay? Let's start from the left. 15 seconds comes down. If you add 36 and 30, what do you get? 66. But that's a degree plus 6 minutes. So you have 6 minutes left. Add a degree here, and what does that give you? Second? 80. 80 on the nose, okay? I don't know whose nose, but on somebody's nose. So the noon altitude of the sun on June the 21st, this is 20, ew, goodness gracious, okay. 21 June, there's the sun, way hot in the sky, okay? That will be 80 degrees, 6 minutes, and 15 seconds. Noon altitude of the sun at our location. Right? You see it? Okay. So let's move down to October 15th. What is the noon altitude of the declination of the sun on October 15th?
8 degrees.
8 degrees what? South. So what do we do there? We subtract the 8 degrees from the 56, blah, blah, blah. Boy, this is getting crowded in here. We'll drop 8 degrees from there. So what would that be? 48 degrees, 36 minutes, and 15 seconds. Right? Everybody got it? I don't have 56 degrees, 36 minutes, 15 seconds, and subtract 8 from it. 8 degrees on the nose. And that would be 48 degrees, 36 minutes, 15 seconds. Okay? So that's on October what? 15th? Okay. 15 October. Okay, they seem to like 15 something. Okay? Well, on 2 of them anyway. And then what's the next date?
December 22nd.
Yes. Down there it's pretty flat, the analemma is, so it doesn't really matter what day it is. But what's the approximate declination of the sun? Hint about as low as it'll go. Say again?
23?
23 degrees, 30 minutes. Okay, about as low as it'll go. And that's south of the equator, so that'll be subtracted from the 56. So let's do it again. 56 degrees, 36 minutes, 15 seconds. And this time we're going to subtract 23 degrees because it's south of the equator, 30 minutes. And what does that give us? $33 degrees, 6 minutes, 15 seconds. That's as high as it'll get right before Christmas. I mean, not very high in the sky at all. Okay? So, you got that for our location, all three of them. All four of them. Declination of the sun and the noon altitude of the sun at our location. Okay, now we're going, this is the time of year to do it if you're going to do it, we're going to move to Altegard, Norway. Okay? I think I'm going to erase a bunch of this. Now, these calculations will be easier because rather than reading off an atlas and giving really precise reading, we're going to be, I've got to change this. Ooh, messed that up, didn't I? Okay. Sorry, I shouldn't draw so much on here. It takes me too long to erase it. Maybe I should have just started over from scratch. It would have been much quicker. Okay. All right, we're now going to be at Altegard, Norway. So here's our globe here. And they tell you the useful piece of information. What do they tell you about Altegard, Norway?
The latitude.
It's what? 70 degrees north is your latitude. So if this is where you are, that's the celestial equator is going to be something pretty close to that. 70 degrees north. Okay, so this is the equator here. So that means the celestial equator is down here somewhere. So there's 70 degrees north. Okay? So what's the theta angle above this? This is celestial equator. What's that? 30? 20. Okay, 20 degrees. Okay. That's how far celestial equator is above the southern horizon in Altegard, Norway. Okay. Pretty close, huh? All right. Now, we already have the declinations. Read them to me. What's the declination of the sun relative to the celestial equator on February the 15th?
13 degrees south.
Second? 13 degrees south. So you have to go 13 degrees south of the celestial equator. So here's the sun at noon on the 15th of February, right? Yeah. So how high is that above the southern horizon? if this is 15 degrees below the celestial equator, is that what you told me? No, you said, say again? 13 degrees. Okay, sorry. I didn't think you said 15. I can't get my eraser to come up. There it is. 13 degrees south. So how high it is above the southern horizon? Should be able to do that in your head. The celestial equator is 20 degrees north of the southern horizon. The sun at noon on February 15th is 13 degrees below the celestial equator. 7 degrees. That's at noon. That's as high as it gets. 7 degrees. And it's not up there for very long either. I mean, those are very short days. Okay, so noon altitude of the sun at Altaguard on February 15th is 7 degrees. 7 degrees. So June 21st, what's the declination of the sun? 23.5 degrees north. So that would be up here, 23 degrees, 30 minutes. And there's the sun on the 21st of June. Okay? So how high is it above the southern horizon on that day? Help me, help me. Second? Oh boy. Okay. It's 23.5 degrees north of the celestial equator. The celestial equator is 20 degrees above the southern horizon. So what would that be? 43 degrees, 30 minutes. Very good. Okay? You got it? Second? Well, you tell me. The celestial equator is 20 degrees above the southern horizon, and the sun is another 23.5 degrees above the celestial equator. So what would that angle be? 43 degrees, 30 minutes.
Why would it be 13 lower than a half?
What's that? Well, you can say in a half a degree or 30 minutes. See, 1 degree is 60 minutes, so a half a degree is 30 minutes. So since I listed the other in minutes, I listed this one too. You can say 23.5 degrees plus 20 degrees would be 43.5 degrees. That would be fine too. Yeah, either one will work. Okay, October 15th. Where is the sun relative to the celestial equator? In other words, the declination. How much? 8 degrees below the celestial equator. So that would be somewhere about, probably didn't do enough. Something about like this. Well, I still didn't do enough. So that's 8 degrees below the celestial equator. So what would be, so this would be, what is it, October 15th?
Yeah.
Okay, what would be the maximum altitude of the sun at noon on that day?
12.
Yeah, 12 degrees, exactly. So back to the 8. 12 degrees. Everybody see that? And how about December 22nd? Where is the declination of the sun on December 22nd?
23.
Half degrees south of the equator, right? Celestial equator. So where would that be? If this is 20, what's 23.5 degrees south of that?
That would be
Below the horizon. Guess what? You'd never receive the sun. Altaguard, Norway, on December 22nd. Probably on Christmas Day, you'll never see the sun. Might get a little bright right around noon, but not enough. It'll be like dawn, right around noon. Never, the sun never comes up. Yuck, yuck, yuck. So that would be doesn't rise, or minus 3.5 degrees, if that's what you want to call it. Okay. All right. Everybody got that? Okay. I'm going to erase again. Going to start our exercise over. Okay. All right. Question number 6. Rip Van Winkle, y'all know him, right? Awakens from his extended slumber, that's a jumble way of saying it, and asks a passerby what year it is so he can determine how long he slept. Okay? The passerby quickly responds and rapidly moves away. Why do you think that? It's a pretty weird looking dude here. Beard down to there, you know, who probably doesn't smell too good. You know, who knows, okay? So, realizing that a 20-year snooze, okay, might be a world's record, he thinks he should pin down the date as well as the year, okay, because he's just asking what year it was. He moves out from under the tree where he slept for 20 years and measures the altitude of the sun at the latitude of his chosen spot on the Hudson River in New York of 42 degrees. So there's the first thing we know is that his latitude here is 42 degrees? 40, yeah, it's 42 degrees. Okay? Now, so that's the first thing we do. We get that 42 degrees in there. Okay? This is 42 degrees. There's your celestial equator on the Hudson River in New York. Okay? He sees that the altitude of the sun, where it crosses meridian at noon, that would be at noon, his local noon, is 44 degrees above. Oh, wait. If he's at 42 degrees latitude, we need to get this angle here. That's 48 degrees there. You're right. Okay? Okay? But he says that the sun is 44 degrees over the southern horizon. So that's he's almost at it. This is 44 degrees above the southern horizon. So there's the sun on that day. Can you tell me from that what the declination of the sun is? Declination of the sun is how far north or south it is of the celestial equator. That's 48 degrees. This is 44 degrees. Say again? 4 degrees, exactly. Which, north or south? South, okay? So we know that the sun is 4 degrees south of that's the declination of the sun. So turn back to our analemma, find 4 degrees south, go across, and you find 2 dates. The first date you run into there is October 4th, and you go on across the analemma, and you see you're really close to March 'What date would you say?
More than 9?
Actually, it's past that. Closer to 15. Huh? Okay. 4 degrees south. Oh, you mean this one? because you see February is going from the 1st of February to the 28th of February. That's in that way. Then March starts with the 1st through the 31st.
The 13th.
I would say maybe not the 13th, maybe 11th. Don't you think? Is that one day past the 10th? The 10th begins with a white line, the next line is so want to guess about 11th? If you're anywhere close, that's good enough. So it's one of those two dates. What did we say? October what?
8th.
Don't think it was that far. 4th, October 4th or March the 11th. So put both of those dates down. On what two possible dates could he have awakened? October what? 4th and March 11th. Now he happens to look up at the tree and sees that the buds are appearing that on the tree he slept under. So what time do you think that would be?
March.
That would be March. So what's the date of his awakening? March the 11th, you said?
Yeah.
Okay. Yeah, there's two questions. What two possible dates could he have awakened? You list them both, and then on what was the actual date of his awakening, that would be the March date. All right. Okay. Now, turn back to the analemma, but keep your finger on the analemma and read on page 377, that paragraph right about the middle of the page. As we saw previously, the analemma graphs the daily difference between clock noon and apparent noon when the sun crosses the meridian. As an example, check the analemma in that they have the figure wrong. They say figure 4.3 is really 48.4. I mean, they really got it bad. Okay? But back on page 374, and they say that on October 15th, which I think we were there before, they say that if you go up from there, straight up that line, you'll see that you're 14 minutes before clock noon. So anything to the left of the 0 minutes, that's before. Anything to the right is afterwards. See that? Okay. So, for the dates given in the table below, use the analemma. This time they got the 48 right, but they still missed the 3. That should be 48.4. To determine whether the actual sun will cross the meridian before or after clock noon and by how many minutes. Okay? Now, in the middle column there, all they want you to write is before or after. Okay? In the far right column, that's where you put the amount of time. So let's find January 10th. And what is are you before or after? That's all you ask to begin with. Before or after. Remember, October the 15th was before. So, yeah, January the 10th, did it say? Yeah, it's definitely going to be after. So that middle column by January 10th, that's after. Now, the amount of time after clock noon. So go up from January 10th, straight up, and say again. Look like to me it might be 7 minutes. That's what I thought. 7 minutes. So before it goes in the middle column, 7 minutes in the right-hand column. So find February 15th. Seems like we've been there before. Before or after? After. And then go up from there, and what do you get? How many minutes?
14.
I'd say it looks more like 14 to me. 14 minutes. Okay? After clock noon. Let's go to April 15th. Tax day. Oh, we don't think of that. April 15th. April 15th? It looks like it might be just a few. Say again?
1 minute.
Well, I'd say even less than that. A few seconds after clock noon. It's still on the right, isn't it? Okay. So I would say after and a few minutes. It's not, no, I'm sorry, a few seconds. It's not even a minute. A few seconds after clock noon. So if you want to say on clock noon, you can say it, okay? How about July the 30th? Before or after? After. And how many minutes? What did you say?
3.
Okay, July 30th. That's not, you're looking at June 30th, I think. July is over, starts on the 5th, 10th, 15th.
6 minutes.
About 6 minutes. That looks like about 6 minutes. After. September 1st. Say again? What you think? There's the 5th, 4th, 3rd, 2nd, 1st. Say again? Okay. Do you count the 5 as being the one between, just below 5 is white and just above it is black, or is it the one that just below it is black and above it is white? You count it right there on 5 minutes. So let's count it there. So count back from there. 4th, 3rd, 2nd, 1st. If you count that, it looks like you're just past on the after side, isn't it? Okay, after, and again, just a few seconds. You're less than a minute. Maybe 30 seconds. Okay? There was September 1st. Boy, everybody's late here. Let's do October 30th. What is it on October 30th? Before or after? Before! We finally got it before. It's an early bird here. On October 30th, what is the number of minutes? No, I don't think so. Wait, you're right. I'm sorry, I was looking at September 30th. And what did you say? I'm looking at the right one. October 30th is one below October there. That's on the second line in, right? If you go up, that's at 16 minutes, isn't it? Is it 20th or 30th?
15 minutes.
Oh, it's the 30th.
30th. Oh, she's trying to throw me off, huh? Okay. Yeah. Okay, she was looking at the 20th. Okay. So that finishes 376. Wait a minute. That finishes 377, right?
You didn't give us the sign, because I said it wrong.
Okay. What did you say?
I said 14.
I know, but then when you changed it.
16.
16 minutes. 16 minutes. Okay? Yeah, that's the people at home, I guess. Finally, number 8 on page 378. Oh, my goodness. Are we going to finish early today? Oh, how can it be? This isn't allowed, is it? Let's stretch this out. No. All right, number 8. All right. Determine the altitude over the southern horizon of the actual sun and the time when it crosses your local meridian on the dates in the table below. So, altitude of the sun over the southern horizon And this is your local meridian. So this is our. So we go back to Bessemer. Don't you love it? Okay. Should have jumped over and done this. Well, no, we didn't have the experience to do it then. Okay. Do you remember our? Yeah. 33 degrees, 23 minutes, 45 seconds. Okay. So up here we'll do, what's that? Yeah, north. Okay. So this will be our alpha, which is our latitude, 33 degrees, 23 minutes, 45 seconds. So we have to determine again what that was. This is celestial equator. This is the equator here. So what's that angle down there? You remember from before, or shall we resubtract? You tell me. Subtract? What do we subtract it from? And which we express as 89 degrees, 59 minutes, and 60 seconds. That's 90 degrees. Subtract from that 33 degrees, 23 minutes, and 45 seconds. And what do you get? 56 degrees, 36 minutes, and 15 seconds. Okay? So that's 56 degrees, 36 minutes, 15 seconds. All right. So we want the altitude of the sun on May 15th. What does our table give us? Did you say 19? Looks like 19 degrees which? North. Okay, so we need to put 19 degrees north. Here's the sun on, what was that, 15 May? I have a good memory, it's just short. Yeah, 15th of May. And that was, how many degrees you say? 19 degrees further north. So what is our altitude of the sun that day? Second? No, you add it to the, to what? 56, yeah. So add it to 19, or add 19 to that, and you get 75 degrees, 36 minutes, and 15 seconds. Okay? That's the altitude of the sun. You want to do the time now? Since you are looking at the analemma on that day. What do we say, May 15th? Are we before or after? And how many minutes? How much? 4 minutes. And 4 minutes before noon would be? Uh, 11:56 in the morning. 11:56 a.m. Right? Okay. Let's move to June 15th. Do we need to look it up, or can we write down what the, say again? What? Okay, got it? June 21st, was it? second? Oh, June 15th? Oh, yeah, you're right, June 15th. So we need to look it up and see what the declination of the sun is, and what is it? Look, well, no, it looks like more like 23 on the notes from the 15th, right?
Yeah.
On the 21st, it'll be in a half. I think that's maybe closer to June 15th. 23. So we're going to add not much more. This will be 23 degrees north. So that would be 79 degrees, 36 minutes, 15 seconds. Okay? And what time does the sun cross the meridian? 0 minutes. So guess what? Neither before nor after, so it'll be 12 o'clock noon. It says what time? Neither before or after. It'll be right on 12 o'clock noon. You can set your clock by it. Okay? How about November 4th? Yep, I'd say 15 degrees is your declination, which is north or south?
South.
South, okay, 15 degrees south. So that means you draw 15 degrees below this. May not have drawn enough. 15 degrees below the celestial equator. So what would we do then? Subtract. So let's subtract this time. I'm going to erase this. Okay? Subtract 15 from 56, and what do you get? 41 degrees, 36 minutes, 15 seconds. That's the altitude of the sun at noon. And what time will that happen?
16 minutes after 12. Oh, that's wrong.
Is it before or after? It's what? Remember they said before. So did you say 15 or 16? Which did you say? Okay, what day are we talking about? I lost it. November 4th. Okay. It looks closer to 16 to me, doesn't it? So 16 degrees before noon would be, 16 minutes before noon would be?
Maybe 11.
16 degrees. 16 minutes.
11.
11:44. Okay, close, but not there. And on Christmas Day, jingle, jingle, what's the declination?
23.
That one looks a little more like 23 and a half to me. Awfully close. Okay? So 23 and a half degrees below the celestial equator, somewhere here. 23 degrees, 30 minutes below celestial equator. Okay? So I'm going to I could have left that one. Okay, 23 degrees, 30 minutes. Okay, I've been putting my doubles for minutes. I don't know what I'm doing. And you're subtracting now. What does that give you? 33 degrees, 6 minutes, 15 seconds. Okay? And what time?
12.
It looks awfully close to 12 noon. It may be a few seconds before 12 noon, but that's close enough. 12 noon. All right. Sad to say, I'm cheating you out of some of your tuition dollars. Okay. Y'all, this is a lab. You can't work together. You have a question? Number 2? If I can find number 2. Was it number 2? Number 2 is the one with no question, so there's no answer. Okay? You can read it. And that's all you can do. Well, they never got around to asking a question. Yes? Okay. On December 25th, the altitude of the sun? Okay. That's the one I just calculated here. The sun is 23.5 degrees below the celestial equator, so you subtract this from that. Can you see it, or is that globe in your way?
I see.
Okay. Any others? If you need to take it home and work on some of your math or something, you can. Or if you finish it, you can turn it in. What's that? Probably not many. I can't remember what they are, but I don't. In this course, there's very little math involved. There's stuff we're doing like this, and we'll do a lab that has a little bit of division in it and stuff, measurement lab. But most of the labs are just more concepts, and most of the tests are concepts. I'm sorry, I guess so.
I think you're great.
I don't think I can keep Adam here. He's on his way. Okay, good deal. Thank you. All right. Please don't write me up.
It's been a long week for you, pal.
What's that?
I said it's been a long week for you, so I know you're tired.
I still got another class tonight. Physics class. Good deal. Was the lab worth it? Do you feel like it's beneficial?
Yeah.
Nobody got off the knee here?
Yeah.
Good deal. I have another Woods in another class, so if I ever get your name crossed up, that's why. His, I think, starts with J too. See, his name is Julian Woods. So,
If I got curious, so when you go to the Birmingham campus,
yeah.
so you won't see Mr. King with you.
No, I go to East Campus.
So you campus.
Yeah. He's on the West Campus.
Oh.
But it's not far, but I can go over there after my class, but I can't guarantee he's still there.
Oh, yeah,
Like I
yeah.
said, he's working short days.
I'll try to email him again because I don't know, he's bored or not.
My guess is he's just not checking his emails.
Did you mention somebody, essay or something we gotta do?
What's that again?
Yeah, mention somebody, essay we gotta do.
Yeah, there is a research paper, yeah.
When is that due?
It's due by the end of the term, but don't wait till then. Get started and get going on it early so you can give me a really good paper and you can get a really good score.
You said it's like 2 pages long.
1 to 2 pages is what you shoot for. If you go longer, it doesn't hurt you. If you're too short, it does hurt.
Like anything about
That, yeah, you can do astronomy, geology, meteorology, oceanography. Yeah, there's tons of topics, tons of people. Yeah, I mean, there's lots of things to choose from.
all that. But you can't do your research on a person that
That person that's contributed to it, yeah, that'd be a good thing. Yeah. Yes, ma'am. I may have, but I haven't seen it. Oh, I
sent it to you yesterday on
No, I haven't.
why I was going to be my grandmother just had surgery. She had a doctor's appointment.
Uh-huh.
And you have doctor's appointment at 11:21. Be there. And she was like, what? And then she was like, oh, you're going to have to take me. And I was like,
That's all right. You got here in time for the class. Barely, but you got here.
I came this
So-
morning for my first class because I have like a quiz. I went in there, but I had to be there at 11:20. The class starts at 10. I went in there at 10, took the 10-question quiz, left. Then we had to like speed
Wow.
up to St. Vincent's.
Right.
And then
Oh, man.
we went back home so I could drop her off. And then I got my car and I came back.
Wow.
And now I'm fixing to have to leave from here and go to work. And I'm like, can I just
Oh,
go to
no.
sleep?
Yeah,
I just
yeah,
want to
of
go
course.
to sleep. That's all I want.
Man. I forgot to mark roll on the lab part. Let me see. Ed was still here.
Yeah, and even though I had told you, I hope to make it at least the last hour of class.
Right.
Because I didn't know what time we would get out.
Right.
It wasn't until 11:20.
Right.
Appointment, so. And I was like, well, I mean, by the time she's finished with that, class gonna be like halfway through.
Right.
I was like, well,
But you got here for the lab part. That's good.
yeah.
Okay.
And like I was telling him, like I asked him what it is, and he said that it was just finishing chapter 15 and starting on chapter 16. And I was like, well, I can read the chapter.
Right.
And then PowerPoints here.
Right.
On what I was like, I'll be fine.
Okay.
It's
Good
fine.
deal.
I'm fine. Everything's fine.
Okay. Good deal. Jessica missed it. Christy was here. Chris missed it. Guy missed it. Kayla. Is she here?